So we went through a couple of examples of mass spectra and what we can take away from the basics of the spectrum itself, right? So we've talked about the M peak, we talked about the base peak, we talked about the rule of 13, we talked about the equation that I can use if I have the isotope abundance of the M and M plus 1 peaks. So we went through just a ringlet of different types of, or a ringer of different types of example problems. And what I want to do now is I keep focusing on the fragmentation pattern. Right? I mean, I keep talking about this over and over and over because, again, many people believe that as long as they have the M peak, then the M peak can identify the compound. And the answer is no. I can't stress that enough. The M peak is just a very small part of the entire picture that we get from a spectra or a spectrum of a compound. So, yeah, we do use the M peak, which is the formula weight of the compound. But we've already seen before, there's tons of different things that can weigh the same amount. And the fragmentation pattern is what's going to help us determine these differences. So, for instance, up on the screen, I'm just going to bring up my calculator and I'm going to pull this over to the side. I want to do a formula weight for a couple of these compounds over here in the center of the actual slide itself. So, what I want to do is I'm just going to do kind of a quick nominal formula weight. So, 12 times 9 plus 14 times 1 is 14, and that gives me 122. All right, then I go down to the next one. That's an entirely different compound. It has 2 nitrogens with it, right? So 7 times 12 plus 10 plus 14 and 14 is going to be 122. All right, let's do the third one. This is 9 times 12. 9 times 12 plus 10 from the hydrogen plus 16 from the oxygen. That's going to be 134. All right, so I'll pull it up again. 7 times 12 plus 6 plus 12 and 12 is 114. C4H10O4, 4 times 12 plus 10 plus 16, 16, 16, and 16. That's 122. And then 12 times 4 plus 10 plus sulfur, which is 32 and 32, is 122. So if we just use the M peak, the only ones that would stand out here would be the C7H6O2 and the C9H10O. And the reason for that is because these formula weights are different, 134 and 114. So that would be an M peak, that would be an M peak, and we could distinguish those two compounds from the rest of the batch. The problem here is that the top two and the bottom two examples, they're all the same. We have 122 for the M peak for all 4 of those. So the M peak is not going to do us any good. Again, when you look at mass spectra, the M peak is a great place to start, but it's not going to give you the answers to everything. Now, there's a way that we can do this. A lot of people are thinking, well, mass spectroscopy, if you can't use the formula weight of a compound, then, what's the purpose of it? Well, yeah, fragmentation pattern comes along as well. But some of you are probably thinking, well, nominal mass. We've never really did nominal mass before when we've used formula weight. So what would happen if I actually brought in not rounded numbers? So for carbon, let's use the entire 12.01. And for hydrogen, let's use the 1.01. And then for nitrogen, let's use the 14.01. So is that going to change our numbers any at all? Well, let's do it. Let's do it for the first 2 examples. So 12.01 times 9 plus 14 times 1.01, which is 14.14. And this gives me 122.23. All right, so in parentheses, I'm going to put 122.23 out here to the side. And then we're going to do the same thing for the next one down. All right, so I'm going to take 12.01 times 7 plus 10 times 1.01 is 10.10 plus 14.01 plus 14.01. And this gives me 122.19. Now, the next question. Well, if mass spectroscopy can calculate formula weights of molecules and fragments, then why can't it distinguish between a 122.23 and a 122.19? Because if it can go these decimals, then these do have different formula weights. And we maybe could use that one to help identify the molecule a little bit better. Well, some instrumentation can. You're on the right track. Good for you. You're thinking. And this concept is called resolution. How resolute is your mass spectrometer? So if you take a look at different compounds, and here are some examples, we're going to see that all of these have in common 122 out in front, all the way across. And if I look at the last 4 digits, those 4 digits are going to be different in every single case. Not just the 4 digits, but if I just go to the 2 decimal places, I'm going to see some differences. 0.10, 0.08, 0.07, 0.03, 0.05, 0.02. They're different. They're not identical. They're not the same. So if I have a MS system with very high resolution, then I will be able to expand the formula weight numbers from the nominal masses. I can actually carry this formula weight out to a decimal place, or to 2 decimal places, or to 3 decimal places. You get the picture. The problem is that resolution, as you can expect, requires money. The higher resolute your mass spectrometer is, the more it's going to cost you in the end. So, here's the drawback. Do you bring an instrument into the laboratory that can do nominal masses without a problem, and that would be able to distinguish the differences between those similar formula weights with the fragmentation patterns? Because again, remember, everything has its own fragmentation pattern, and even if they give you the same fragments, they will come in different abundances. We saw that before in a previous example. Or do you spend a little bit more money, $10, $20, $30, $50, $60,000, depending on what it is, in order to go out 1 decimal place or 2 decimal places? So that way your machine can feel a little bit better about identifying the compound that has been injected. So here's an example problem that you might see on a test, just to kind of drive home the concept of what nominal mass means. So it says, what is the nominal mass and the exact mass of C4H10N2? All right, well, we kind of already done this, but we're going to split the page up in half. So C4H10N2, carbon, we're going to do nominal mass first. So carbon is 12.01, but I rounded off to a 12. Hydrogen is 1.01, so I rounded off to a 1. And nitrogen is 14.01, but I rounded off to a 14. Remember, nominal means whole number. Well, I have 4 of these, and I have 10 of those, and I have 2 of these. So I'll do a little bit of multiplication here. And then I add up everything. And that gives me a total of 86. 86 grams per mole. That would be the nominal formula weight of that compound. And if I had a cheap mass spectrometer, then that's what it would see, and that's what it report. And many of the mass spectra that we will see as example problems will give you nominal masses like this, 86. They round it all off. Now, what about exact? Well, exact would be the formula weights like we've always done them. There is no change here. So most of the time we would bring out at least 12.01, 2 decimal places for formula weight at least when we do them. Hydrogen would be 1.01, and then our nitrogen would be 14.01. Well, I bring in the multipliers just like before, times the nitrogen by 2, times the hydrogen by 10, times the carbon by 4. And then we're going to add up everything, and I'm just going to do this kind of in one step all the way through. I'm not going to break it down. So 12.01 times 4 plus 10.10 plus, that's going to be a 28.02. So I hit enter, and I'm going to get 86.16. So notice the whole numbers are going to be the same. You're not that far off from the formula weight. That's why nominal mass is accepted. But what we're leaving off with the nominal masses are the small decimal places that happen here at the very end. So if you see this example problem on a quiz or an online test, maybe a paper test in the end, this is what nominal mass means compared to the exact mass. It's just more detail. How much do you want to carry that number through? Almost like significant figures in a way, just a different way of looking at it. And this is where we get the concept of what we call resolution. So folks, here's an example of another mass spectra, or spectrum of a compound. And what we're looking at here, again, what I want you to focus on are the whole numbers that are present. So 15, 27, 41, 43, and it looks like we have a 122 and a 124. So all of these are nominal masses all the way across. We don't really see any decimal places. If I had a better instrument, I could increase my resolution. I could report these numbers with 1 decimal or 2 decimal or 4 decimals at the end. It just really depends on the type of machine that I have. Okay? Something else that I kind of want to take some time and review is what kind of data can I basically take away from this? Well, look at over here at the very end. This is an M peak, 122, and maybe an M plus 2 peak at 124. And if I look here to the sides, I'm going to see really tiny little bitty signals. And those are coming from more isotopes that might be present. But we've got an M and an M plus 2 peak. So what this basically means is that I could have a halogen into the picture, because we said that these lines will not look like this. If this was an oxygen, which is also an M plus 2 peak, we said that those would be kind of smaller. And then chlorine also has an M plus 2 peak, but it's about 1/3 of the height of the M peak itself. And we said that when we've got bromine, that also has an M plus 2 peak, and these are going to be the same size or the same height, or close to it at least. And that's what we're seeing right here, right? Those two lines are about the same height, and that's a very clear-cut signal that this is probably going to be a brominated compound. I have bromine that's tagging along with it, and if I look up here at the structure, yeah, sure enough, there we go. There's bromine. All right, another thing that I want to review is this one. This 43 is what we would call the base peak, right? So that means that this is the most common fragment. When that molecule, because it's the highest, when that molecule goes through the electron beam, it is going to split into 2 pieces. And we need to know where that 43 is going to come from. All right, so I'm going to basically take this compound, and I'm going to figure out how I can get 43 from the thing. All right? Now, if we look at the periodic table, we're already going to know that if bromine stays behind, we are over the 43 atomic weight. I mean, bromine weighs much larger than 43, so it's not going to work for us. Bromine cannot stay behind in our fragment. So what I'll do is that I'll say, all right, well, if we get rid of this bromine, and let's say that we cleave the fragment right here, and this bromine goes off on its own, how much do we have left over here? So that's 12 and 12 and 12, which is 36. And then we have another 3, 4, 5, 6, and 7. So if I add these two numbers up together, what do I get? 43. So that means that that fragment is coming from that propyl group that is carrying a positive charge. All right, so that's where the base peak is coming from. That's what I can get from the M and the M+2 peak. I can't really use the rule of 13, though, because it's not a true hydrocarbon here. I can't really use that isotope abundance equation because I don't have that data at my disposal, but I can at least use some of these other things from the mass spectra itself to figure out what this compound possibly could contain. All right, now let's take a look at some of these other options. Let's say that I cleave the molecule here. That is a 12, 13, 14, 15. So that will give me a positive charge right there. So if I come down here, well, here is the 15. And this is coming from my CH3 with a positive group. All right, so if we do that, I'm going to erase these just so this stuff doesn't get too complicated. And now we're going to cleave it again. This time I'm going to change the color just so we can keep track of it. So let's kind of cleave it at this spot and figure out what type of components could I get from the picture. So let's say the positive goes on this side. Well, that's going to be a 12 and a 12, which is 24, 25, 26, 27, 28, and 29. So we do see a 29, but it's actually not the one that's listed. A 27 is listed, not a 29. So this might cause some confusion. And then you might go, okay, well, let's see. What if we don't put the positive on that side? What if we put the positive here on this side? Okay, well, let's start with bromine at 79, and then we add another 12 to it, and then we add another 2 to it. All right, so what do we get in that case? We're going to end up getting a 93 if you do the math. All right, well, on the scale down here at the bottom, if we go to 90, 91, 92, 93, look, we do see a signal, and that signal's present. There's 95, and there's 94, and there's 93. So with the 93, though, it's not even labeled on the spectra, so that's not even enough to kind of place an importance on. So the question is, where does the 27 and where does the 41 come from? So this is going to give us rise to things are going to fragment in a particular way. And some will have rules that they have to go by. We've not talked about any of that yet. The only thing that we have done is that we've just taken a very simplistic look at a molecule and just chopped it up into two pieces and said, well, in this case we get it, and in this case we get this number, and in this case we get that number, and we've just kind of assigned and identified what peaks are representing what parts of the structure. That's been it. So there's more to this to come, and I want you to be prepared for that. Okay, so 27 we haven't identified yet. 41 we have not identified yet. And we saw that on some of our earlier massed spectra as well. All right, here's another MS spectra. It says, what is the structure? Carbon, hydrogen, and bromine only. Now, this is a different type of question. First, it tells me that bromine is listed. And I would see that right up here at the very top. This would be my M peak. This would be an M+2 peak. And this combo of the same height, pretty much, is going to represent bromine. All right, so I know that bromine is going to be present. The other atoms are going to be carbon and they're going to be hydrogen. So I know that this has got to be kind of my condensed structure. I just got to figure out how many I have. Okay, well, if this is the M peak right there, it looks like this is going to happen. There's 100. Here's 110. So 1, 2, 3, 4, 5, 6, 7, 8. It looks like the M peak is 108. All right, well, if bromine is present, right, because this question says what's the structure. If bromine is present, then what that means is that we have already taken up some of this formula weight. And this formula weight is going to be 79. So I'm going to take 108 minus 79, and I'm going to get a 29 that's left over. So I have about a 29 wiggle room that I can bring in carbons and I can bring in hydrogens in order to make it add up to be 108. All right, well, if I add on a carbon, that's going to take away 12 from that number. If I add on another carbon, it's going to take away another 12. So this is 24. Well, 24 from 29, how many do I have left over? I've got 5 left over. That's perfect, because this carbon would need 3 hydrogens to be happy, and this carbon would need 2 hydrogens to be happy. And then if I added up all of the formula weights, the nominal masses, 12 and 3, 12 and 2, and 79, I would get 108 as the formula weight. So this gives me an M peak of 108. It also gives me an M plus 2 peak because bromine is involved. There's the structure. I don't know what it was in the beginning. Have no clue what was in that tube. We shot it into the MS. We picked up that there was bromine involved. We knew that the remaining pieces were carbon and hydrogen from other tests that we did maybe in a laboratory. And guess what? Just by using the MS, we were able to determine the structure of the compound. There's no other way that this molecule could be hooked up. That's the only choice, right? If you put the bromine on that end, or if you put the bromine on the front end, it does not matter. Sorry, folks. You're not going to change anybody's opinion, and it's the same structure whether you put it on the front or the back. There's no other option, period, point blank. All right, in addition to that, what if this molecule cleaves? What if the molecule cleaves right here? What do we get? Well, let's kind of play around with the fragmentation pattern. So I've already answered the question. What's the structure? There it is. All right, we're just going to go on to the next step. Well, this would be 12, and 12 is 24, 25, 26, 27, 28, and 29. This would give me a 29 fragment. Well, if I look on the screen, here's 30, and look at here. There's 29. This big old line right there is my base peak, and that base peak is the most common fragment that the detector sees, meaning, because that's the highest one. Now look, the whole compound as a whole, that's pretty high as well. That's not too shabby, but that one's going to beat it out. That one is going to be relative to the 100 mark, which means that that's the most common fragment. When this molecule goes across the electron beam, it will split up into 2 pieces, and it will prefer, when it does that, to stick this positive charge with this fragment, my CH3 CH2 fragment, and bromine will be left behind on its own. Now, why would that want to happen? If this molecule crosses the electron beam, why would I see that molecule prefer to split the way that it does? Well, first off, you have to understand the rules of electronegativity. Electronegativity means electron greedy. That's what that definition basically says. It is an atom that loves to have some electrons, and that means a negative charge. And if it can find those electrons out there, it's going to reach out, grab them, and keep them as much as possible. On the periodic table, fluorine is the most electronegative. And then as you go from fluorine to the left or as you go from fluorine down, your electronegativity decreases from that point. Fluorine is the most electronegative on the element or on the periodic chart. Bromine's not that far behind. Bromine is electronegative. That means he's electron greedy, which is why this bromine is okay carrying that negative charge. So if the molecule has to make a decision to split up in two pieces when it goes across the electron beam, it is going to make that decision knowing that bromine is electronegative, and it will prefer to have those electrons, and it can take them and it can run away, and bromine will be very happy if it does it. And then we've left this positive charge onto the remaining fragment that's left behind, and that is this ethyl group that weighs 29. See, folks, all of this stuff in general chemistry about electronegativity and periodic trends, all the stuff in organic chemistry about electronegativity and reactions and negative areas on the molecule, it's all coming back, and it's maybe all coming back to bite you if you didn't get it in the first time. All right, here's another MS, and it says, what is the M peak, and then what is the structure? First, I'll go over here to the right-hand side, and you might see this as 80, and you might say that is the M peak. And under a normal circumstance, it will be. The problem is that there is a larger peak that's right here, and this is at 78. And look, whenever I see this happen, I see an M and an M plus 2, then I've got to really step back for a minute and say, okay, do we know anything else about the compound? Is 80 the true M peak? Or is 80 an M plus 2 peak, with the 78 being the formula weight for the compound? So normally that M plus 2 peak would be very tiny. It would be almost as tiny as what some of these others are going to be, right? I see very small, faint, weak signals right here. And that's normally what the M plus 2 peak would be. The problem is that this is a little larger. Well, if I didn't know that it has chlorine, then I probably would be very uncomfortable making this decision. In addition to that, though, if I look at 78 and 80, the M and the M plus 2, I see that one is a 9 and one is a 3. That's 1/3 of that number, right? 3 times 3 is 9. So this would be kind of a dead giveaway almost. If the true M peak was 80, then I would not have a neighboring peak that would be anywhere near the numbers that are there at the end. They will be much, much smaller. But in this case, I have a 78 and 80 that are 2 apart. 80 just so happens to be 1/3 the height of the 78, which is a very good sign that chlorine is going to be involved in the structure. So that means that 78 is going to be the M peak. All right, over here to the side, I'm now going to take 78, and I've just added chlorine to it. So chlorine weighs 35, and I'm going to take the difference between these two numbers. I'm going to see what we have left over. And that will leave us with 43. So now I've got to think about how many carbons and how many hydrogens could we bring into this picture to get 43. Because again, we want to know the structure of the compound that was introduced to give us this MS. All right, well, if I add in 1 carbon, that's 12. If I add in 2 carbons, that's 24. If I add in another one, that's 36. I'm getting closer, right? So if I add 3 more hydrogens, that's 37, 38, 39. This is 40, 41. And this is 42 and 43. So I can feel pretty good maybe with this scenario here. And I can say, well, there's your structure. It's C3H. I'm going to do the condensed structure up here. C3H. There's a 3, 4, 5, 6, 7. And chlorine. Okay, that's great. But look, I've drawn it this way. Someone else, though, could come behind me and draw it a different way. Instead of taking the chlorine and popping it out on the end, they could take a chlorine and squeeze it there in the middle. Have enough hydrogens to make everything have 4 bonds, and there you go. It's the same deal. I still have 3 carbons. 1, 2, 3. I still have 7 hydrogens in total. 3, 4, 5, 6, 7, and 1 chlorine. So this is option number 1, and this is option number 2. We've not really made it that far yet. Both of these have the same nominal mass. Both of these provide me with a 78. Both of these provide me with things that would work. The difference would be the fragmentation patterns. Those frag patterns would be different. One would frag a different way than the other. And we've got to look at the frag patterns on the MS to determine which one of these would be preferred. So that means I would have to go back to the drawing board here, and we're not going to do that in this example. We might do it in the next video, but here we have a 25, 26, and 27. Here we have a pretty large line. There's 40, 41, 42, and 43. Here we've got a larger line that's 60, 61, 62, and 63. And it looks like I can start assigning numbers here to maybe help me figure out which way is going to be the best. Which one is going to match up to the frag pattern of the molecule the best way. That will help me to determine my choice. But here in this case, it just asks for the structure. There's the condensed structure, C3, H7, Cl. Might not be able to figure out how these guys hook up yet, but at least to know how many are actually going to be present. So in the next video, we'll talk about frag patterns, mainly of the alkyl halides first. We'll start there in the beginning. Notice we did talk about some of these with hydrocarbons. They had no functional groups on them. It was just carbon and hydrogen, and it was very simple. We just kind of went down the line and said cleave here, and then we'll cleave there, and then we'll cleave here, and we just try to figure out how many different numbers that we could get from it. Alkyl halides are a little different. They will cleave a certain particular way. And before we answer which question, is it route number 1 or route number 2 here, we've got to understand how they prefer to fragment to begin with. So that's what we'll do next. So stay tuned. Go take a break. I've rambled on for 30 minutes about a chlorine on a mass spectrum. But, you know, that's just the nature of the beast. So go get a beer. Go get a drink. Go get some chips and salsa. I'll be here when you get back.